In this video, I'm going to go over AP Precalculus topic 312, equivalent representations of trigonometric functions, which primarily just includes different trig identities, which are a way that we can represent different trig functions equal to other trig functions in different equations. So starting with the basic trig identities. First, the reciprocal identities. So cosecant is the reciprocal of sine. So cosecant is equal to 1 over sine. Secant is equal to 1 over cosine. And cotangent is equal to 1 over tangent. The ratio identities are the equivalent forms for tangent and cotangent. So tangent is sine of theta divided by cosine of theta. Cotangent, which is the reciprocal of tangent, is cosine over sine. Next, we have the Pythagorean identities. So picture our unit circle. We have our circle with a radius of 1 centered at the origin. The x and the y value are equivalent to cosine and sine. So in this, starting with the Pythagorean theorem, thus Pythagorean identity, we know that x squared plus y squared is equal to 1 squared. Well, my x is equal to cosine of theta, and my y is equal to sine of theta. Okay, so I can rewrite this as sine squared theta plus cosine squared theta is equal to 1. This is the first of 3 Pythagorean identities. I'm also going to write 2 equivalent forms of this one, of just kind of this statement rewritten in 2 different ways. Once solving for cosine, so if sine squared plus cosine squared equals 1, we can isolate sine squared by subtracting cosine squared. And then the same thing with cosine squared. These aren't different identities, it's just different rearrangements, but they're very, very common. If I see 1 minus cosine squared, I can replace that with a sine squared, or 1 minus sine squared, we can replace it with a cosine squared, or vice versa. There are 2 other forms for this one. If I take sine squared plus cosine squared equals 1, and divide both sides by sine squared. Okay, looking at each individual thing, sine squared divided by sine squared is going to be 1. Cosine squared divided by sine squared. Cosine over sine is cotangent, so cosine squared over sine squared is cotangent squared. And then 1 over sine is cosecant, so 1 over sine squared is cosecant squared theta. And then we can do the same thing with cosine squared. So if I divide everything by cosine, sine squared divided by cosine squared is going to be a tangent squared. Cosine squared divided by cosine squared is 1. And 1 over cosine squared is secant squared. So these are our Pythagorean identities. You definitely want to know sine squared plus cosine squared equals 1. These ones are going to come pretty automatic. These 2, I think it's easy enough to derive if you need to, but it's a good thing to know that there's some relationship between tangent squared and secant squared, cotangent squared and cosecant squared, and we could subtract 1 and isolate different trig functions here. But those are our Pythagorean identities. We can do different things with this Pythagorean identity, these identities. So we can go back to our little triangle here and come up with our relationship between x, y, and 1. So x squared plus y squared is equal to 1. I can solve each of these for x and for y. So y is going to be the square root of 1 minus x squared, and x is equal to the square root of 1 minus y squared. Okay, and I'll derive 1. This is just sort of like a bonus Pythagorean identity for the inverse trig functions. So if I wrote this in terms of, so if I do cosine of theta in terms of x, that's going to be adjacent over hypotenuse. which is x over 1 or x. If I do the sine of theta in terms of x, that's going to be y over 1, but we said y is the square root of 1 minus x squared over 1. Well, I can solve each of these for theta. So then I can set each of these equal to each other. So cosine inverse of x is equal to the sine inverse of root 1 minus x squared. I'm not sure how much you need to get into this, but this is just something that we can arrive at using those Pythagorean theorem again. Let's go back to our main identities. Okay, so we're going to rewrite the expression g of x equals 1 over cosine times 1 minus sine squared as an expression in which cosine appears once and no other trig functions are involved. Okay, so we're just going to kind of sort through this. First thing I see is 1 minus sine squared. Cosine squared plus sine squared equals 1, so 1 minus sine squared is equivalent to a cosine squared. That makes this cosine squared x divided by cosine, which simplifies down to cosine of x. So we can use those identities to rewrite, to simplify these expressions. Okay, same question, just now we're writing this whole guy involving powers of sine. So that kind of gives us a clue as to where we're headed. I like to write all my trig functions in terms of sine and cosine. So I'm going to rewrite that tangent as sine of x over cosine of x. Okay, well, the cosine on the top and the bottom cancel. So I'm left with sine of x minus sine of x cosine of x, cosine squared. Okay, now here you have options. Okay, option number 1 would be to rewrite this cosine squared as a 1 minus sine squared, because I know I'm trying to get sines. But I'm looking at this and I see I can factor a sine out, which will leave me with a 1 minus cosine squared. So this is going to be sine of x times sine squared x, which gives me sine cubed x. But here's that alternative path. If we had turned the cosine squared into 1 minus sine squared, distribute the sine, makes that a sine, or minus sine, and a plus sine cubed. Those two signs cancel, and we get the same thing. So with these trig functions, there's definitely different strategies that we can use. Okay, next we're going to be solving sine squared minus cosine squared, and we're going to solve for j equals -1 on the interval 0 to 2 pi. So we've got sine squared x minus sine of x minus cosine squared x equals -1. Okay, when I've got a squared term and I've got a linear term, it ultimately means we're probably going to be factoring. But we've got two different trig functions here, which makes that challenging. So I'm going to go ahead and replace this cosine squared with a 1 minus sine squared. Okay, so I can go ahead and distribute that negative. Okay, then I'm going to combine my like terms. So I've got a sine squared plus a sine squared, which is a 2 sine squared, minus a sine of x minus 1 equals -1. Well, if I add 1 to both sides of this equation, we're going to have 2 sine squared x minus sine of x equals 0, which we need when we're doing factoring in order to do our 0 factor product. So I'm going to factor out a sine. Okay, we'll set each of those equal to 0. If I solve 2 sine x minus 1 equals 0, we're looking for where sine of x is equal to 1/2. And we're looking between 0 and 2 pi. So inclusive, sine is 0 when x is 0, pi and 2 pi. Sine is equal to 1/2 at pi over 6 and at 5 pi over 6. Next we have the sum and difference identities. I'm not going to derive these for you. You can certainly find these derivations. I'm just going to provide a counterexample to what you may intuitively think is going to happen and how it doesn't actually work that way. I'm going to start with sine of pi. I'm going to rewrite that as sine of pi over 2 plus pi over 2. Okay, that's perfectly valid. I can break that up. What I'm going to show you, when you see parentheses, you've just been trained to think about distribution, but that is only in multiplication. Things like trig functions or powers or logs or anything like that, the parentheses, it's not distribution, only multiplication. But you see these parentheses and you're like, hey, I know distribution. Okay, well, sine of pi over 2 is 1. So we're saying sine of pi is 2? No. Okay, sine of pi we know is 0, that y value there. It can never equal 2. So the bottom line is we can't distribute. Distribution does not work there. But I will go ahead and provide the sum and difference identities for you. So again, there's a whole derivation for these, but we have the sine of a sum, the sine of a difference, the cosine of a sum, the cosine of a difference. So sine of a plus b is sine a cosine b plus cosine a sine b, and these can be switched in order. The only difference between here and here is if this is a plus, this is a plus. If this is a minus, this is a minus. For cosine, it's a slightly different pattern, but it's still kind of that combination of sines and cosines and a's and b's. So cosine a plus b is cosine a cosine b minus, so if this is a plus, this is a minus, sine a sine b. Cosine a minus b is the same exact thing, except for if this is a minus, this is a plus. So one way you can kind of condense all four of those is sine of a plus or minus b is sine of a cosine of a plus or minus cosine a sine b, or cosine a plus or minus b is cosine a cosine b minus plus, to give that emphasis on its opposite, sine a sine b. So those are sum and difference identities that we need to know. Okay, so I'm going to find the exact value of cosine 7 pi over 12. So what I'm going to do is rewrite that 7 pi over 12 as the sum of two other angles that I know some information about. So I'm going to rewrite this as 3 pi over 12 and 4 pi over 12. Because when I reduce each of those, we get 3 pi over 12 is equivalent to pi over 4, and 4 pi over 12 is equivalent to pi over 3. Now I'm going to do my sum and difference identity for cosine. So it's going to be cosine pi over 4, cosine pi over 3. If this is a plus, this is a minus. Sine pi over 4, sine pi over 3. And then we just use our unit circle to evaluate each of these. Cosine pi over 4 is root 2 over 2. My x value at pi over 3 is 1/2 minus sine of pi over 4 is root 2 over 2. Y value at pi over 3 is root 3 over 2. So when I multiply, we're going to have root 2 over 4 minus root 6 over 4. And I can't combine those two different roots. So we're just going to say root 2 minus root 6 over 4. Okay, this says show that the quantity cosine pi over 2 minus x is equal to sine of x. So I'm going to use my cosine identity here, which will be cosine pi over 2 cosine x. So this minus, all that dictates is that in the middle here, we're going to have a plus. And then it's going to be sine pi over 2 sine of x. Then I'm going to evaluate cosine of pi over 2 is equal to 0. At the top of the circle, our x value is 0. Sine of pi over 2 is 1. So when I simplify this, 0 times cosine is 0, 1 times sine is sine. Okay, the function m is given by m of x equals cosine x plus pi minus sine x plus pi. Find all values in the domain that yield an output value of 0. So I'm setting the whole equation equal to 0. Okay, and then I'm going to write out two different expansions. I'm going to do this in different colors to illustrate this. Okay, so this one is my sum and difference for cosine, which is going to be cosine x cosine pi minus, if this is a plus, sine of x sine of pi. And then we're going to be subtracting. I'll do this whole second part in red. So sine is sine x cosine pi. If this is a plus, for sine it's the same. And then it's going to be cosine x sine of pi, so just the opposite there. And we're solving when this equals 0. Well, all of the cosine pi's and sine pi's have values. Okay, so we're going to have cosine of x. The cosine of pi is a -1. Sine of x. The sine of pi, our y value of pi, is 0. Let's go ahead and distribute the negative. Okay, so we're going to have a minus sine of x. The cosine of pi, again, is -1. I'll do it. The sine of pi is still 0. Okay, so I'm going to have a minus cosine of x there. That's going to give me a 0 minus a negative sine x. Okay, so to solve this, I'm just going to move the cosine over and do some thinking here. Okay, so when we're solving a trig equation, we want to start with thinking, on the unit circle, what are these values? So where does sine of x equal cosine of x? Well, that's going to occur at in the first and third quadrant, right? Because sine is root 2 over 2 and root 2 over 2 in quadrant 1. So that's going to be pi over 4. And then again at 5 pi over 4. Okay, but we want all of the values. Okay, well, pi over 4 is here. 5 pi over 4 is here. So I can go from here to here to here to here by doing pi over 4 plus pi k will give me all of my values. I would believe it's also acceptable just to say pi over 4 plus 2 pi k and 5 pi over 4 plus 2 pi k, where k is an integer. Next we have our double angle identities. So I'm going to go ahead and derive these for you. Okay, this is if we take the angle and we double it. Well, I can rewrite this 2 theta as theta plus theta, and then use my sum and difference identity. So sine is going to be sine theta cosine theta plus cosine theta sine theta. Well, sine times cosine is the same as cosine times sine. So this is equivalent to 2 sine theta cosine theta. Okay, and then we'll do the same thing for cosine. Cosine 2 theta, I can rewrite as cosine theta plus theta, and then we can do the sum and difference for that one, which will be cosine theta cosine theta. If that's a plus, this is a minus. Sine theta sine theta, which I can rewrite as cosine squared theta minus sine squared theta. that's going to be kind of my main one, but I have two different variations on this one, where if I take the cosine squared and replace it with a sine squared, okay, I can simplify this to 1 minus 2 sine squared theta, or I can take the sine squared and replace it with the 1 minus cosine squared. So minus minus makes that a plus. So I can rewrite this as 2 cosine squared theta minus 1. Those are just kind of different variations. But if you know this first one, we can get to the second too. So those are my double angle identities that we want to know for our AP exam. So I've got k of x equals 1 minus cosine 2x times secant squared x. And I want to write this in terms of powers of tangent and no other trig functions. Okay, well, the first thing I want to do is automatically replace this with our identity. So that's going to equal, I'm just going to start with cosine squared x minus sine squared x times secant, I'm going to write as 1 over cosine squared. Okay, so this is, I'm multiplying this times this, so I'm going to go ahead and distribute this to both of those terms. I'll just leave the 1 there for now. So I'm going to have a cosine squared x over a cosine squared x minus a sine squared x over a cosine squared x. So that's going to be 1 minus cosine over cosine is 1, and then a negative times a negative is a positive. Well, sine squared divided by cosine squared is tangent squared, and 1 minus 1 is 0. So I write this as tangent squared x. So always starting with that identity, if we see cosine 2x or sine 2x, that's our first move. Okay, our next one, we've got sine 2x plus sine, and we're going to solve for g equals 0 on the interval 0 to pi. I'll go ahead and set up my equation. Okay, there's no way to combine these. I have two different angles here. Whatever this angle is, this is double that angle. But I can use my double angle identity for sine, which is 2 sine x cosine x. Okay, now we're going to factor. I'm going to pull out my common factor of sine. So we're solving for where sine of x is equal to 0, and when this factor equals 0, which doing some quick algebra in my head, subtract the 1 and divide by 2. We're looking for cosine to be negative 1/2. So sine of x is 0 between 0 and pi at 0 and pi. And then cosine is negative 1/2. Our x value is negative 1/2 at our 2 pi over 3. And that's it between 0 and pi. Okay, my last problem is a version of our free response number 4. And I'm going to talk a little bit about what you can expect there. It will pull from units 2 and 3. I am just going to do a unit 3 trig only version. But on your AP exam, it's going to include exponential functions, logarithmic functions, as well as our trig functions. These are the directions that you're going to see every single time. So it's a good idea to get familiar with that. Things like if you can do it as an exact value, like log base 2 of 8, you can't leave it like that. You have to evaluate it, cosine pi over 2, and so on. So just make sure to spend some time reading this so that when you get to your AP exam, you don't have to worry about it. So question 4 is going to be 3 parts. You're going to have part A, which is going to give you 2 equations, part B, which is going to give you 2 equations. Again, here I've done just trig. On your AP exam, this is going to be a combination of logs and exponents, exponential functions, and trig functions. Both sines, cosines, inverses, all that can be there. Part A and part B, one of them is going to tell you to rewrite each expression. The other one will tell you to solve. If the first one is a rewrite, the second one will be a solve. If the first one is a solve, the second will be a rewrite, and they'll be matching. The third, and it's going to be increase in difficulty, is going to be a solving problem where you're going to find where some output value is whatever. So let's run through this one. This one I did my rewrites for the first part. Again, that could be, it's a 50-50 whether it's going to be solve first, then rewrite, or rewrite, then solve. So this says rewrite G as an expression in which cotangent appears once and no other trig functions are used. Okay, so I have this. I'm going to go ahead and turn it all into sines and cosines for a little bit. So cosecant is 1 over sine. Secant is 1 over cosine. Tangent is sine over cosine. Okay, so here, this is 1 over sine of x cosine of x. And I want to get a common denominator so I can subtract these. That means I'm going to multiply this by a sine over a sine. That's just a 1, but it allows me to get that common denominator. Sine times sine is sine squared. And we get our common denominator of sine x times cosine of x. When I combine those, we get 1 minus sine squared x in the numerator, and hopefully there's a little alarm ringing in your head saying, hey, 1 minus sine squared equals cosine squared. Okay, well, a cosine squared on the top divided by a cosine is going to give me a cosine of x over sine of x, which is equal to, good news, cotangent of x, since that's what I was trying to get here. Now, there might be like plus ones or something like that, but in this case, it boiled down to just cotangent. Okay, our second one. Okay, first thing that I see is I'm going to go ahead and factor out a 2, because that gives me something I'm sort of familiar with. Okay, 1 minus cosine squared is sine squared. If it's flipped, it's going to be opposite, but if you don't want to memorize that, which is fine, I can replace cosine squared with 1 minus sine squared. Okay, well, in the parentheses, the 1 minus 1 cancels, so we're going to have 2 times a negative sine squared over a sine. And then that simplifies to a negative 2 sine x. Okay, second is going to be my solving. Okay, so I'm solving sine squared plus sine equals 0 on the interval 0 to 2 pi. Okay, so simple factoring here. So I'm looking for where sine of x is 0 and where sine of x is negative 1. Okay, between 0 and 2 pi is going to be 0 and pi, not 2 pi, how this interval is written. And then here, sine is negative 1 down at the bottom of our circle at 3 pi over 2. Next one, we're going to solve for when this one is equal to 3. So we'll divide and take the square root. When I do, it's going to be plus or minus square root of 3 over 2 when I take the square roots. So between 0 and pi, we're looking for our long x values, which is going to be at pi over 6, and our negative at 5 pi over 6. The last one tends to be the most difficult. Here it involves a double angle identity. So I'm going to set this whole equation equal to 0. Okay, we have 3 different versions for this one. I'm just going to do the main one, and then I can change it if I need to. So this is going to be replaced with cosine squared x minus sine squared x. Okay, well, sine squared minus sine squared, that's going to cancel. And then we get a factoring. So factor out a cosine. So either cosine of x equals 0 or cosine of x equals 1. Okay. So let's think about this. Cosine is 0 the first time at pi over 2. And then it's going to be at 3 pi over 2 and back up. So it's going to be pi over 2 plus pi k. Cosine is 1 at 0, so 0 plus 2 pi k, or we can just say 2 pi k. I think both of those are acceptable. We do want to add, though, that where k is an integer. Okay, so that was 312, all about different trig identities, our sum and difference identities, our Pythagorean identities, our double angle identities, all of which you need to have memorized. Thank you for watching.